Welcome to this video in the Atomic Theory chapter. This is 3.41, more about electrons. Today what we're going to do is cover 3 short mini lessons that are based on what you learned about electron configurations in our previous video. We are going to go beyond 5p and present to you guys the Aufbau diagram, which is otherwise known as the diagonal chart, SPDF Electron Configurations of ions, and introduce to you the concept of Isoelectronic Species, and teach you how to write Noble notation, which is also known as abbreviated electron configurations. If you haven't already done so, please make sure you have your chemistry notebook handy. You're going to need a pencil, a periodic table, and this little baby, which is called the diagonal chart or the Aufbau Matrix. You're going to need that to write some electron configurations. So without any further ado, let's get started. So we're going to begin today's lesson with a quick review of what we covered in our last video, where we talked about the fact at the very end that the electron cloud model of the atom has these electrons that reside in these sublevels that are incredibly tangled as you get further up out away from your nucleus, and the nucleus would be considered in relation to your sublevels here. And that's going to make the order of filling a little bit difficult to remember when you are writing electron configurations. Now, if our periodic table looked like this, that was right there, which is called the long form periodic table, it might be a little bit easier to remember. You still have to remember what each one of these blocks are, that this would be 3D, and this would be 4D, etc., and this would be 4F, and this would be 5F, and then the order actually is okay. But because we can't remember that, it tends to make things a little bit more difficult. So to help you remember the order of filling and make your job a little bit easier, I'm going to teach you guys a quick cheat which you can use to write electron configurations correctly and never miss the order of the sublevels that fill. Grab your periodic table and come with me. Let's say I asked you to write the electron configuration for mercury, and that is element Hg, which, if you look here, is buried deep within the periodic table. This is in 3D, 4D, 5D. If you recall, doing this just with a periodic table is not so easy, because at some point the sublevels and the blocks here wind up overlapping and are no longer sequential. So what scientists did is they developed something of a cheat sheet for you guys, which is called the Aufbau Matrix or the diagonal chart, because, no spoiler, look, it points diagonally. But anyway, back to this. This chart that you see here is the ultimate, simply because this is going to help you write your electron configurations and keep the order of filling straight. Let me show you how this works. Let's say we want to write the electron configuration for mercury. Well, mercury isn't 5D. It is the last element in the block, so it is 5D10. So I go to my matrix here and I find 5D, and I write down that it's 10. That means, based on everything that we learned so far, all the sublevels that are underneath 5D have to have filled before 5D does. So we have to write the electron configuration for each one of these quantum numbers and sublevels. So now what we're going to do is use these arrows to help us with the order. The first thing I'm going to write, like I would in any electron configuration, is 1s. How many electrons fill the s sublevel? There are 2. The arrow points this way. Now we got to go back to here. Now we're going to fill the 2s sublevel, 2s2. And so this is actually giving you the order to fill. So we follow the arrow and then we go back to the top. Now I'm going to fill 2p. Now I'm going to fill 3s. And now I'm going to go back to 3p. Now I'm going to go from 3p to 4s, which is 2. Now I'm going to go from 4s to 3d, and this is where we start to get out of order, but this Aufbau matrix is helping us keep it straight. Now I'm going to 4p, 4p6. Now I'm going to 5s. Now I am going to 4d10. Now I'm going to 5p6. Now I am going to 6s2. And whoop, there's our F. I don't know if you remember from the last video, but there are 14 elements in the F block that are not shown here. So when we exhaust the placement of electrons, it'll be 4F14. And then we come to 5D, which is where our mercury is. It is the 10th element there, so we would write 5D10. And what we have is the electron configuration now for mercury. And we did that without having to memorize all the disorderly quantum numbers and sublevels that are here. We use this Aufbau matrix. So one of the things you have to do is actually learn how to create this matrix so you can use it as a cheat sheet on a test. So this is something that you would commit to memory and then write down when you've received your test paper. So let's go jump over to the virtual blackboard and teach you how to do this. All right, welcome to the virtual blackboard, and what we're going to do here now is teach you how to create the Aufbau matrix. So in order to do so, the first thing we have to do is we have to list our sublevels. So we are going to write S, leaving yourself a little bit of space, P, D, and F. And now once you have done that, what we're going to do is come down here, and we are going to now write our principal quantum numbers. 1, 2, 3, 4, 5, 6, and 7. Now at this point, we want to fill in the matrix, and we have to do so with a little bit of our knowledge of atomic theory. Think about this. In our first principal energy level, we know we only have an S sublevel, so we're going to write 1S. In our second principal energy level, we know we have an S and a P, so we're going to write 2S and 2p. So we're creating a matrix that works sort of like this, that takes one from the y-axis here and one from the x-axis. We know in our third principal energy level we have 3 sublevels, 3s, 3p, and 3d. In our fourth, now we know we have all the sublevels. We have 4s, we have 4p, we have 4D, and we have 4F. And we know from here on out, every principal energy level has all 4 sublevels. Once you have this, now you are ready for the next step. So here is a cleaned up version of our matrix. And what we're going to do now is put the diagonal lines in. So the assumption that we are going to make is that we are going to fill sequentially. So we're going to start with 1s. Then we're going to start with 2s. Then from 2s comes 2p, then 3s. And here is where the matrix starts going through and starts to become helpful. And so what we notice is we start to just put our arrows through, and all of a sudden we have the order of filling. So what we've done is we've created our very own Aufbau matrix, which we can use as an aid on a test when we are going deep into the periodic table. Welcome back from the world of the virtual blackboard. Here is a quick summary of everything I did using the Aufbau matrix to actually write those electron configurations. So if you'd like, you can pause the video now, copy this into your notes, and then unpause when you got it, because we're going to try some. All right, the first element that I would like you to write the electron configuration for using your newly acquired skills and your Aufbau matrix is indium. Indium is the 49th element, and it is buried deep within the periodic table. So pause the video now, use your matrix, and write the electron configuration. When you're done, hit pause and check your answer. Okay, if you did this one correctly, here is what you should have gotten. So make sure you check your work. Make sure you did indeed find that indium was in 5p and was 5p1, and you filled all of the rest of your sublevels accordingly. Now the big test. This is your turn. There are 5 electron configurations for you to write. Some are way deep in the periodic table, so make sure you use the matrix for this. Pause the video now and then unpause when you're ready for the answer. All right, if you did this correctly, here's what you should have gotten. If you didn't get it right or have any questions, make sure you note them, and we will certainly address them tomorrow. The next portion of our video revolves around how to write something called noble notations. These are essentially shortcut SPDF electron configurations. Some people would call them abbreviated electron configurations. Let me show you what these are all about. So let's say I asked you to write the SPDF electron configuration for bismuth. That is Bi, it is element 83. Now you guys have seen from writing the previous practice questions that once you get deep into the table, the electron configurations get too long. So there is a way to shorten your work. So you will need your periodic table and your Aufbau Matrix, and we're going to just dive right in. The way noble notation shortens your work is by using noble gases as a jumping off point. So we know that bismuth is in 6p, and that is located right here. Go up one period and find the noble gas. That would be here and would be xenon. Now the assumption is that noble gases are noble because they have a full valence shell. So what we're going to do now is we are going to put xenon in brackets. The brackets mean that I have filled all the sublevels that have come before xenon. We're talking from hydrogen all the way up. Now, xenon is in 5p, so that is right there on our filling diagram. So since now everything is filled up to 5p, we can continue on with our Aufbau matrix. So we now have to fill 6s, and we know it would take 2 electrons. And then we have to fill 4f, which would be 4f14. Then we go to 5d, which is 5d10. And then we get from 5d to 6p, which is where bismuth is located. So now we got to say, well, where in 6p is bismuth? Well, it is 6p1, 6p2, 6p3. And so what we would do is then write in 6p3, which is the only unfilled quantum number and sublevel that we have here. And look, this has shortened our electron configuration tremendously. All right, before I set you free to try some of these, I want you to copy down the summary of how to write your noble notation. So commit this to your notes by pausing the video now and then unpause when you are done. So the first example I'd like you to try is for the element cadmium. So that is the 48th element that is there. Try to write the noble notation, pause the video now, and then unpause when you got an answer. If you did this one correctly, you would have gotten Kr in brackets 5s2 4d10. Let's try another one just to be sure. Please write the noble notation, the abbreviated electron configuration, the shortcut for barium. Pause the video now and then unpause when you're ready for an answer. All right, if you did this one correctly, there really wasn't much to it. It is xenon in brackets 6s2. One note for the guys in my class, if you are planning to use this on every element, like let's say, I don't know, like lithium, and you were like bracket helium and then 2s1, no. Can't do that. So the only time that it's okay to use this is when your elements are above xenon. That said, you may see textbooks that use this far lower down in the periodic table. But remember, in our class, we are now building skills, and I got to make sure you can actually write electron configurations. So as long as it's above xenon, you're golden. Now, moving on, we're going to start to talk about electron configurations of ions, and this is our last topic in the video. As a reminder, to predict the type of ion that any atom is going to form, we have to look at the oxidation number in the upper right-hand corner of the box on the periodic table. So with that, we can see here, sodium has a +1 charge, magnesium +2, oxygen is -2. And you may be wondering what to do when we actually don't get the New York State periodic table that has all of those, and we get something sort of like this that doesn't have them at all. Well, one of the things that you have to do is you have to remember the oxidation number is all about what the atom has to do to reach a stable octet. So for instance, going back to here, we know sodium's got to lose its 1 valence electron. So once it does that, it winds up having 8. Magnesium has to lose its 2 valence electrons. Oxygen, which has 6, needs to gain 2 electrons to wind up getting 8. You just got to remember when you get a periodic table like this that the group numbers that we see up here match the number of valence electrons you have, and then you can give yourself a rough estimate of what these elements have to do to get a stable octet, whether they have to gain electrons or they have to lose electrons. And it's usually, this is the barrier here in group 14, or what we call group 4A, where they go from losing electrons to gaining electrons. So these guys are all going to have to lose 1, lose 2, lose 3, variable what they do, and then the most common charges here are gain 3, gain 2, gain 1, and obviously our noble gases don't do anything, because they're noble, and they already have a full valence shell, full S&P outermost sublevel. So in order to write the electron configuration of an ion, you have to consider first what the SPDF electron configuration is of the atomic form of that element. So here we have phosphorus, and we see that the Bohr notation is 285. Let's turn that into SPDF. And here it is. It's 1s2, 2s2, 2p6, 3s2, 3p3. Now we have to say to ourselves, what is this phosphorus atom going to do when it becomes a phosphide ion? So I take a peek at my oxidation numbers, and I look at the very first one, which is the most common ionic state, and I see that it is a -3. Remember, negative numbers here mean you are gaining electrons. So the 3 that we see here, well, that gets zipped, and we're going to pick up 3 more electrons. We're going to go from a total of 3 electrons in our p sublevel to a total of 6. And that is going to give us a phosphide ion, which has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. So you simply have to alter the last sublevel's number of electrons based on what the charge is on the atom. Before we move on, let's just cover what happens when you have a positive ion. Here we are trying to write the electron configuration for a lithium ion. So we want to write its original SPDF electron configuration, which would be 1s2, 2s1, short and simple. Now what we want to do is we want to look at the most common ionic form. We see here it is a +1. That means I am going to lose 1 electron. So now I have to take this electron configuration, which is here, and I got to modify it. Before we added to the total number of electrons in that last sublevel, in this case, because there is only 1 electron and we are going to lose it, the entire sublevel now gets deleted because there's no electrons left in it. And that gives us an electron configuration simply of 1s2 for a lithium ion. So the big takeaway here is when you have negative ions, you are going to add electrons. When you have positive ions, you're going to take them away, and you most likely will have to delete the entire sublevel that was previously there. So now it is your turn. There are 5 atoms that are here, and I want you to write the electron configuration for the most common form of the ion that these atoms will turn into. Pause the video now while you do that, and then unpause when you're ready for the answer. All right, if you did this correctly, here is what you should have gotten. So check your answers carefully. Make sure you added and subtracted in the right places for your electrons. And in the cases of the 4 positive ions, you needed to remove a principal energy level. In the case of the bromide ion, which is here, you actually needed to add to the electron total. So piggybacking on the lesson on ions, I want to drop 2 more nuggets of information on you. This first one surrounds something called isoelectronic species. So to illustrate that point, please write the SPDF electron configuration for the following 3 species that are here. Stop the video now and then unpause when you got it. All right, if you did them correctly, you should notice that, wait a minute, all 3 are identical. And furthermore, the 3 of them have an electron configuration that resembles that of a noble gas, which, if for all of you playing along at home, the noble gases are your group 18 atoms. The other thing I would like to call your attention to here is that we will notice that all 3 of these electron configurations are matching. We would say that the oxide ion and the sodium ion are isoelectronic with neon, or these 2 species here are isoelectronic with one another. So anytime you have matching or shared electron configurations, we would say the species are isoelectronic. The last thing I want to call your attention to surrounds valence electrons. In all of your previous science classes, you guys should know that chemical reactions happen, and usually that gives an atom 8 valence electrons, which makes it inert. Inert means unreactive. That's the whole goal, is to get those 8 valence electrons and achieve noble gas status. Of course, unless you wind up looking like helium, in which case you don't need 8 electrons, you need 2. But I don't want to digress. Looking at that in Bohr notation is easy because you just look for the 8 electrons in the outermost shell that's there. But when you are dealing with SPDF, it is not as simple. So what we look for in SPDF, when we want to see if we have a full valence shell and our element is inert, we will look for the outermost level, which is always represented by the highest principal quantum number. So take a look at calcium here. The highest principal quantum number is not 1, is not 2, is not 2, it's 3. So we have 3 here, but we also have 3 here. The valence electrons are the sum of the s and p electrons in the highest principal quantum number present. In this case, we have a 3s and a 3p. We have 2 electrons plus 6, which gives me my 8 valence electrons. That means that this is inert. Same with bromine that we see here, except we're getting deep into the periodic table, so now we have overlapping d sublevels. But fret not, we want the outermost level, which is represented by the highest principal quantum number. The highest principal quantum number here is a 4, and I see it twice with an s and a p. So it is always your outermost s and p sublevels you see. We have 2 in the s and 6 in the p for a total of 8 electrons. The bromide ion fulfills the octet rule and is inert. So that is pretty much it for me. I hope you guys got a lot out of this lesson. And of course, as we always say, if you do have burning questions that are on fire, make sure you bring them to the burning questions segment during our next session. It has been a pleasure taking you through more of atomic theory. I look forward to catching y'all on our next video. See you on the flip side. Peace out.
That's all, folks.